so we were about to prove, so we had proved that actually for the Anderson model at large disorder. So we looked at the Anderson model. H omega equals minus Laplacian plus lambda v omega. V omega, I write it in this way, is omega gamma on the diagonal. Right, so this is on L2ZD. And we have proved that theorem, there exists lambda 0 positive such that for lambda larger than lambda 0, the spectrum of H omega is made, omega almost surely, is made only of pure point spectrum. Right. We actually got something slightly better than that because we remember we have proved that there exists some constant eta which was positive such that if we look at the expectation value of the sum over the gammas in ZD of e to the eta times gamma, and we take here the element gamma 0, delta gamma, h omega minus e inverse, or e plus I0, say, inverse delta 0, and this to the power 1/2. We have shown that this sum actually is finite. Right, this expectation is finite for almost all E. No, actually for E, we have even something better. Let me think. How should I write it? What's the best way I want to write it? And this, yeah, okay. The best way maybe is that sup over E in C, and you can remove this, right? Part of E non-vanishing, for example. Right, so we can actually take E to the real line, okay? So we got an estimate like this, with a constant eta that we can compute it directly from the, right? We had actually an upper bound on the expectation of this, right, which was exponential. So if you take, for example, we had the expectation of the upper bound of this was less than e to the minus something times gamma, right? If you take the something divided by 2, multiply, you get that the thing converges, everything is fine, right? So we get something like this. So now, what we want to prove now is the following thing. So this, what does it tell you? It tells you that for almost every E, right, on the real line, if you look at the resolvent kernel, it's of course, when you take this expectation, right, I can get, what I can do, I can use just the ergodicity to transform this, to replace the 0 here by any beta, right? And so what I get is that if I fix a beta, right, I get the same expectation with, and here gamma is going to be the distance between gamma and beta, right? I get the same thing. So what I see is that if I look at this matrix has off diagonal exponentially decaying coefficients, right? The coefficients, so the matrix is nicely localized. And so what we're going to prove now is that this is not only true for the Green's function, but it's actually true for any rather nice function of the operator h omega. So this is what is called the dynamical localization. So the proof I'm going to present is due to Michael Eisenman. The proof of the former theorem I present actually was originally due to Eisenman-Milchanov, but what I actually presented is due to Barry-Simon. So under the same assumptions, assume the omega gamma are IID with bounded, compactly supported density. That's the only thing. Then there exists lambda 0 positive, such that for lambda larger than lambda 0, one has the following. So actually there exists lambda and eta positive, right? Such that if you take the expectation of now the soup in time of the matrix elements of what? Delta gamma e to the I t h omega delta 0, right? Well, I'm going to take the same thing, take the expectation of the sum e to the eta times gamma, sum over the gamma in ZD. This is finite. Right, we can write it in this way. Right, the thing is finite. So what does it mean? It means that if you look at the evolution, right, the Schrödinger evolution associated to h omega, then omega almost surely, the evolution, its matrix, has also this off-diagonal decaying part. And from the evolution, we'll see this a little bit later on, but remark. Of course, once you know this, if you write phi of E is integral of phi hat of xi e to the minus or plus I t xi. So it's not exactly phi. Let me write it this way. Could put the minus here, that's fine. Doesn't change anything, right? It's true for all t, and it's not, yeah, it's true for all t real, so that's fine. The xi, right? So phi is a real function. Right? If you can integrate, if phi hat is integrable, right, you can apply this to phi of this function. Right? And so you get that the kernel of any function of the operator is going to have the same properties. Right? You just take the fact that phi of h omega is actually this integral, e to the minus I t h omega. You apply delta gamma delta 0. One is gamma, one is 0. Right? And you say you get the exponential decay of any function, right? And in particular, one of the things you would like to get the exponential decay of, we come to that later, is the spectral projectors, right? So the spectral projectors cannot be written exactly in this way. Why? Because if you look at the spectral projector on some interval, right? Well, its Fourier transform is going to be sine x divided by x up to a constant, right? It's the Fourier transform of the characteristic interval, sine x divided by x. It's not integrable, in the sense it's not L1, right? Of course, it's integrable in the generalized sense. So you have to work a little bit more, okay? But except for that, essentially you're getting the projections. But once you have found that the projections are exponentially decaying, right? Then it means that actually the eigenfunctions, because if you take an eigenfunction, it's just an image of the projection by itself. The eigenfunctions will also be exponentially decaying. Right? That's one of the ways to prove that the eigenfunctions are exponentially decaying in this regime. And we're going to use this, but I'll give the theorem later on. We're going to prove this later on. Okay, so let's start with the proof of this. So again, we are going to rely on rank 1 perturbations. What did I want to say? Oh yeah, there is one remark I didn't make yet, but which can be of importance here, is that, okay, let me make another remark before I go on. So you have these you have these estimates, right? So let me write them again. Well, you have these estimates. So the other remark is for the restricted operators. Right. So, of course, if you take h omega, so pick lambda inside ZD, large, right? Of course, if I look at h omega restricted to lambda with any kind of boundary conditions, the spectrum of this is going to be pure point. It's a finite dimensional matrix, right? And even if you're dealing with continuous model, the spectrum is going to be pure point because it's a second order differential operator on a compact manifold. So we know that its spectrum is discrete, nothing to that. But the method of proof that we used that gave us this, right? The same method. You can do exactly the same thing. You just replace, formally in each thing, you replace h omega by h omega lambda. Yields the following thing. It yields that the soup over E belonging to C, imaginary part of E different from 0, of the sum over gamma in lambda, E to the eta gamma, so the existence of a gamma and a lambda 0, delta gamma h omega lambda minus E inverse delta 0 minus 1/2. This is finite. And actually, it leads the following thing. You can even take the soup over the lambdas in ZD. So you have a uniform bound. You have a uniform bound on all these resolvents. Right? And in the same way, for the evolution operator, for this one, in the same way for the evolution operator, you get that if you take the soup over the lambda in ZD, soup over, expectation of here there is a mistake. Actually, you should put let me think. No, that's correct. That's correct. You get this. The sum over gamma in ZD e to the gamma eta soup in time of delta gamma e to the minus I t h omega restricted to lambda delta 0. This is finite. Right, you get the same statement, which is uniform over larger and larger cubes. Okay? Just because you can apply exactly the same method, and the bounds that you get show you that it doesn't depend on the cube lambda. So let's prove this. Okay, so again, we're going to start. Remember, we have an operator A, and we have A lambda, which is A plus lambda phi, right? And we assume phi cyclic for A. And our aim now is to understand what our aim is to reconstruct the evolution, right, from the resolvent. Okay, so there are a number of ways to do that, but one of the ways is we're going to use the spectral theorem actually. And by the spectral theorem, we know that So we assume this. So we can associate d mu lambda, right, is just the spectral resolution associated to phi, right? So it is just dE lambda of of A lambda phi scalar phi, right? So just take the spectral resolution of the operator A lambda, okay? So the projection valued measure, and you apply it to phi. It's the same thing, right? Because phi is cyclic. Okay, and so what you have by the spectral theorem, there exists a unitary u depending on lambda that goes to our Hilbert space to L2 R, actually the spectrum, but d mu is supported on the spectrum of A lambda, such that if you look at the image of phi is just a constant function 1, right? And if you look at u lambda, A lambda, so which way? So this is, so here we go from, sorry, it's this way. No, that's fine, yeah, that's fine. U lambda, this is just a multiplication by lambda. Right? That's the spectral theorem. Okay, you have an operator which is of multiplicity 1. The spectrum has multiplicity 1 because you have one cyclic vector, right? And then it means that you have a unitary equivalence between this operator, right, and the operator obtained by the multiplication by lambda on just the space L2 with the measure which is the spectral measure. Right? So if you think, for example, of the case of matrices, this means that this measure is just going to be a sum of Dirac masses. Right?
Lambda is parameter.
Sorry, yeah, lambda here is a parameter, right? So this is d mu lambda. So that's, if you want, d mu lambda of E. E is the energy parameter in R. Right? So this is a multiplication by, by E, not by lambda, you're right. By E in, you're right, in L2 R d mu lambda of E. You're right. That's perfect, that's correct. Lambda here is fixed, okay? So, and what we're going to do now is compute U lambda under the assumptions that, well, the spectrum of A lambda is pure point, right? Okay, so let us recall. So again, let us recall f of E is just the integral of d mu. So this is d mu is d mu 0. Right? Functions that we introduced last time. We have g of E this, right? And we know, we already have seen, we know that, so because you're in the pure point, to say that A lambda is pure point is equivalent to say that E almost everywhere, we have G of E finite. Right? This is actually, A lambda pure point, lambda almost everywhere. Right? This is, I should write it this way. for almost every lambda. This is the same thing as G of E finite almost everywhere. Remember, this was the Simon-Wolf criterion, right? Or actually, rather, what led to the Simon-Wolf criterion. Okay, and if G of E is finite, then we know that f of E plus I0 is alpha exists, right? This limit exists. It's real and exists is alpha. This is real and E is an eigenvalue of A lambda if alpha equals -1 over lambda. Minus, let me check. See, I got something which is. So there was did I forget the minus sign in my notes? Oh, did I change the sign? Oh, no, that's tick tick tick. No, I think it's correct. I just forgot the minus sign in the notes here. Okay, now we're going to use this to understand who the mapping U is. Okay, so the first lemma is that lemma 1. If G of E is finite for almost every E almost every, then for such an E, if you look at the limit of A minus E plus I epsilon inverse applied to phi. So the limit, it's the strong limit as far as epsilon goes to 0 from above. Right? Well, this limit exists. It's called phi of E. So the limit exists. Moreover, if d mu lambda is supported on the set of E such that G of E is finite, let's say in some interval AB, G is finite, then one has that U lambda of psi at E is nothing but minus lambda psi scalar phi of E. Right? Sorry, it's the other way around. This just depends on how you define psi, phi of psi. Okay. So fixed lambda U psi of E should be a function of E, right? This is the function of E inside the vector inside the Hilbert space L2R d mu lambda. Right? So let's prove this. Okay, the basic formula is the following. It comes from the formula that we had for the resolvent of a rank 1 perturbation that we wrote before. Remember, we had, so proof, we had A lambda minus Z inverse minus A minus Z inverse. This is equal to minus lambda A minus Z inverse phi phi A minus Z inverse divided by 1 plus lambda A minus Z inverse phi phi. Sorry, the other way around. Phi A minus Z inverse phi. Right, we had this. So, which can also be written as minus lambda A minus Z inverse phi phi A lambda minus Z inverse. Right, you can write this in the following way. And so this immediately gives you the following thing, is that A lambda minus Z inverse phi divided by phi A lambda minus Z inverse phi. This thing doesn't depend on lambda and is equal to A minus Z inverse phi phi. Right. So we do it first for imaginary part of Z non-vanishing. Right? And for all lambda. Okay. Now, if I said if G of E is finite, well, then we know that f of lambda, f of E plus I 0 exists, right? And well, exists, and I write it this way, is equal to minus 1 over lambda. Okay. And E value of A lambda. Right, this is just because this is vanishing, so we get that it's an eigenvalue of A lambda. Right, and we also know that if you want to compute the projector, what did I write? So what is it I want to show? Okay, so what I want to show is that okay, yeah, what I know is that if I look, because E is an eigenvalue of A lambda, if I compute I epsilon A lambda minus E plus I epsilon, right, minus 1. And I take the strong limit of this just by take the strong limit of this. This is just P E, the projector, right, on E. Let me write it. P A lambda on E, right? This strong limit exists just by the spectral theorem. Okay, this strong limit exists, and it's just a projector on A lambda on the subspace, on the eigenspace associated to E for the operator A lambda, right, by spectral theorem. Right? It's just a spectral theorem. Okay, so if you now do the following, you multiply, you take this equality, star, and you multiply star by I epsilon, right? So you take star times I epsilon, so you get that I epsilon A lambda minus inverse divided. So here I have this. Right? What do I get? So you get, right? You multiply both sides by I epsilon, right? What is happening? So what I want to, so this is fine. The only thing that is missing, let me check. This is not what I want to do exactly. No, so what I want to do is the following thing. So this is 5. Divide by the same thing for I. Divide multiplied by I epsilon A lambda on inverse, and here I have the phi. Right, that is sitting. Okay, and now, what do I know about this one? Okay, now I just want to check this one. So one thing that I have is by this, I know that if I look at phi A minus lambda plus I epsilon, right, inverse phi, this is equal to what? It is equal to A minus E plus I epsilon inverse phi minus what? Minus lambda, and here I have the same thing. So you see, if I take phi here, I get phi here. So here I get, if I put it, let me check now. There is something I don't understand. Okay, let me write out what it gives. What you get here, so here you get minus lambda phi a minus, so I do it with lambda, I know I have z with v. Okay, it's going to be shorter to write with v. Minus phi a minus z inverse phi. This is equal to minus lambda phi a minus z inverse phi times phi. Oh yeah, no, that's fine. A lambda minus z inverse phi, right? This is correct. So this gives you that this is equal to phi. So this gives you that phi a lambda minus z inverse phi. 1 plus so what I want to do is I want the quotient of this. So if I do the if I just do the quotient, what do I get? I get that. Okay, I divide the whole equality by this, right? So I get that 1 minus phi a minus z minus 1 phi divided by phi a lambda minus z inverse phi is equal to minus lambda phi a minus z inverse phi, right? So if I let, but then well, I'm unhappy about one thing. There's one thing. No. So if I let now z equals e plus I epsilon, and I let epsilon go to 0 plus, I know that this one converges to minus 1 over lambda. Right, this is what I wrote, where is it written? It should be written somewhere over there. Yeah, here over there. Minus 1 over lambda. This one is 1, so this one goes to 0, which is not exactly what I'm
lambda. This sign is wrong.
Yeah, I'm wondering whether the sign is wrong, but no, I think it's. Okay, let me check that this formula is correct with this sign.
I think
the minus here is wrong?
Yes, maybe.
That's possible, I agree with you, but let me check first.
You define write this formula for Rho a lambda, where
yeah. No, but
lambda p.
Yeah, but I don't think so. Okay, let me check. But let's check that this one is correct. So, okay. So, what I need to do is the following thing. I want to check that if I multiply this by a minus lambda, I just check what's the correct sign. So what can I erase? I'm going to erase this. Let's check that I have the correct sign here. So I just multiply. I take a minus z inverse minus equals minus lambda. Sorry, a minus z inverse phi. Sorry. So this, yeah, minus lambda. A lambda minus z inverse, and I multiply this by a lambda minus z on this side, right? So, recalling what a lambda minus z is, it's a minus z plus phi. Okay. So this is identity plus lambda a minus z inverse phi, right? That's when you take the first term and multiply by this. Here you have a minus z gives you identity. Here you have plus lambda, and here you have a minus z phi phi. And then the second term is minus lambda a minus z inverse phi. And here you have phi, because this is a lambda minus z, right? So the sign is correct. Okay, this goes away. And this is correct. Okay, so let me try to now see where. No, okay. Well, yeah, okay, I see what's the problem. I see what the problem is. Let me think. Okay, what I announced is, yeah, you see? Okay, what one needs to do is, of course, I should look at the statement that I pretended. I didn't say that it was I epsilon times this that had the limit. It is this. So, up. Let's take, where is it? I should take the I epsilon here, right? And what I need to check is that if I take I epsilon here, I get something. This one should have a non-vanishing limit. Okay? I know that this one has a limit, and I just want to check that this one has a non-vanishing limit. Okay? Because what I pretend is that it's actually this thing that has the limit, right? Not I epsilon times this. It's going to have a limit too. It's going to be 0, but this is not what I want. Okay? So I just need to. Okay, and so. Okay, so let's just okay, now let me what, okay, no, that this computation was correct, but I'm not sure it's useful. I just want so the only thing I want is that oh,
this converts to G?
No, let me check now. How do I get this limit? So what we know is that this one is nice and converges. So we only need to show that this one converges to non-vanishing thing, right? That's the only thing we know, because we know that this one converges to minus 1 over lambda. Okay. The only thing we need to understand is that this one converges to something non-vanishing. Okay. So this is I epsilon, okay, and what is it? It's I epsilon integral of d mu lambda of E minus E plus minus I epsilon.
Oh, we can look into the upper formula.
Well, in this one?
Up.
In this one, yeah?
Yes, more up.
Okay, here?
And substitute.
Yes, you can substitute it, but then you see the problem is that you need to show that the vector that you get here is not orthogonal to phi. Right, so at some point there is something to be done. Okay, if you do this substitution, indeed, you can do that. So the convergence of this is fine, but you want the thing to converge not to 0. Right, that's you want to avoid the problem with 0. So this is, let's separate real part and imaginary part. So this is the integral of E minus E d mu lambda E divided by E minus E squared plus epsilon squared. And here we have epsilon plus integral of I epsilon squared d mu lambda e minus e squared plus epsilon squared, all right? So, well, okay, so this part goes to 0, right? This, sorry, there's no I, there's a, because you had I epsilon, so minus I, it's plus this, right? The I went away because of this one. This one goes to 0 by dominated convergence, right? It converges to 0 almost everywhere. And it's dominated by 1, and the measure d mu lambda is a probability measure. Right, you took phi to be normalized. And we want to know that what the other one does. So it's not obvious to me that this doesn't go to 0. It converges is fine, but I need an argument that the thing doesn't go to 0. What do I know? What do I know to prove this?
Sorry, but when this thing is orthogonal to phi, this eigenfunction is the eigenfunction of A sub 0, and the limit is 0. No?
So you're saying is, so this phi of E is, okay, so assume phi of E is orthogonal to phi. You're right. Then you're right, that's correct. So if I epsilon phi A lambda minus E plus I epsilon inverse phi goes to 0, then we have that P A lambda E phi is equal to 0. That's correct. Right? By what we saw above. Okay. No, sorry. We have that this scalar phi, sorry. This is equal to 0. Okay. And so what we have is that if I take a vector, so we have that. So what you are saying is that if I take
eigenfunction at here and E of A sub lambda is.
So if I take this of H, not of H actually, if I, so just means that just this, yeah, this of H is orthogonal to phi. Right? This means this, because this you can write as a square. This is a projector. You write as a square. It means that phi is mapped to 0 by this projector. Right? So it means that this is actually orthogonal to phi. That's correct. So
this means the eigenfunction
of A lambda associated to E is orthogonal to phi, and so it's also an eigenfunction for A0. That's correct.
And this limit is 0.
So So this implies that P A lambda E, right, is equal or is contained in P A E, right? You have this. These eigenfunctions, so of H, of course. Right? These eigenfunctions, because if I apply A lambda to this or I apply A to this, because it's orthogonal to phi, you get the same result. Right? So it means that PA lambda E of H is contained in PA E of H, right? And so these are eigenfunctions of P of A associated to E, right? Well, I don't see what.
Maybe in this particular case we can calculate.
Uh-huh.
It should be.
Oh, but this is not possible. Yeah, this is not possible. Why? Because we assumed, right, that all the eigenvalues of A are simple. We assume that phi is cyclic, right? So we assume that all the eigenvalues of A's are simple, okay? So what we have is that if you look at the eigenvalue equation that you get from this, right? If you write A1, A2 of A, AN of A, and so on, right? What you get is that when you have A1, E1, E2 of A, then the eigenvalue equation for A lambda is just 1 plus the sum of, if you call the eigenvectors, I don't know, psi n, phi squared, E n A minus, sorry, not this. What you should take is 1 plus lambda sum over psi n phi squared divided by E n of A minus E, E minus E n of A, sorry, minus E n of A. This is just, this thing is just equal to F of E plus I0, right? For sum over all n. And you look at when this is equal to 1. Right, this is just 1 plus lambda times F equals 0, which is what appears in here. Right, this gives you the eigenvalues. But now what you know that this function has a pole at each of these points. Right? So what happens is that the functions look like this. So here below the function is always, below it's always negative. Right? And here the function, so I'm plotting this function. Right? And what we are looking for is when does the function take the value minus 1 over lambda. So you see that every of these gaps contains one eigenvalue, or if you are below, if lambda is negative, you have one here. Okay? And so you see that there are no eigenvalue that can be the same for that and that. So this cannot be possible. Right? So this is indeed ruled out, right? And so it means that this limit cannot be 0. Right? This thing cannot be 0. So once you know this, you get the existence of the limit that you have here. This limit exists. Moreover, the equation that you have here, the equation that is written, where is it? Up here, when you take the limit, you immediately see that if you take this scalar phi, if you take star scalar phi, phi scalar star, this gives you that. Take phi scalar this gives you that phi of E scalar phi, well, converges to what? If you take scalar phi on the other side, you see that it goes away. It converges to minus 1 over lambda. Or this is equal to minus 1 over lambda. Right? Because this part goes away, these two eliminate, and it's only left with this. All right? And the other thing that this proves, and phi E is, as we just said, is an eigenvector of A lambda. For almost every E. Okay, so we know that U lambda of psi at E is equal to psi scalar some eigenvector. Right? Well, no, we know we're going to show this. We're going to show this. Right? Let's show that this. And how should an eigenvector normalized, where chi of E, eigenvector of A lambda associated to E and normalized by phi chi E is equal to 1. Indeed, indeed, you can write A lambda is the sum over E, and now this is not chi lambda because the normalization is not the correct one, right? E times chi tilde E, right? Where chi tilde is norm 1. This is just a spectral decomposition. We know that the thing has only eigenvalues, right? It's the sum over the E's. This. And then we know that d mu lambda by the definition of d mu lambda this is the sum over E of chi tilde E phi modulus square, right? And here you have, sorry, not chi, it's delta E, it's just direct mass at E, sum over the E's. And so U lambda psi at E is just psi chi tilde E. There was one thing missing here. times some function a of e, but we want, but normalized by u lambda phi of e should be the constant function 1. Right? So it means that a tilde e, a of e has to be taken as 1 over phi chi tilde e. And if I define chi of e is equal to what? It's equal to, so I want it to be, I want it to be what? I want it to be ae times chi tilde e, sorry, 1 over ae times chi tilde e. Right, is this, let me think. No, this, sorry, it's ae times chi tilde e. Right, so that this is equal to, well, it's just equal to psi chi e, which is what I want in the end. Then, of course, by definition, we have that phi chi e equals 1. Right? We have that phi chi e equals 1, and that this is expressed exactly in the way I announced. Right? So it's just a change of normalization of the vectors. Okay, that's the first thing. And the second lemma, which is actually the one that is going to get us to the semi-group. So still assume that g of e is finite, e almost everywhere. Right, and so phi equals 1. So lambda is again, lambda is as okay, so let's assume lambda is a random variable with a density g as in the theorem. And assume that A is bounded to make it simple, which is going to be the case in the application. Assume A bounded. Then for lambda 0 in the support of G, we have that if we look at the expectation of the supremum in time of delta gamma e to the I t a lambda delta 0, take this, this to the power 3/2, this excitation to the power 3/2 is bounded from above by a constant times the integral over k is the support, well, k is going to be some large compact, but I didn't write down. Let me check the proof. I didn't write down what the thing is. Yeah. So here we're going to put there exists some r positive, such that the integral from minus r to r. So here, fine, and we get that this is delta. Sorry, this is phi h. A. There's no h for the moment. A lambda 0 minus e minus I epsilon. To the power minus 1 phi 2.5 d e. I can put the 0. Okay, and what's the constant c? C is given in terms of delta, which is the diameter of the support of delta 1/3, and the sup norm of G 2/3, and delta is the sup of support of G minus the nth of the support of G. R is, there exists some R, we're going to see what R is in the proof. It depends on the support of G, right? And actually it depends on the spectrum of A. So what we know is that, so proof, there exists R such that for all lambda in the support of G, the spectrum of A lambda is contained in minus RR. Right? So it's just a global bound for the spectrum of A lambda. So we can integrate, all our spectral integrals can be written in this way, right? And here it's not, this I wrote delta gamma delta 0, there's nothing like this here. Sorry, here there's a mistake, because for the moment there is a psi, and here we have phi. Here we have psi and phi. It's the same psi and phi, and psi is arbitrary. Okay.
Yes.
For any psi length 1. Okay.
Arbitrary operator.
Psi is an arbitrary vector. Yeah, exactly. We started with an abstract operator, right? So psi is any vector length 1. Okay, so this is not. I was already going to the other setting, but it's not the case here. Psi is arbitrary vector of length 1. Okay, and so the basic idea is, of course, the usual thing is that if I write e to the minus I t a lambda phi, then we have the integral formula that this is the integral from minus r to r of e to the I t e, or minus I t e, and here we integrate the spectral measure, right? U lambda of psi, I take it, yeah, sorry, very fine. D mu lambda of phi. D mu lambda of, sorry, of E. Phi. Right, just write. And we know as U lambda unitary and psi is normalized to 1, we know that the integral minus r u lambda psi squared d mu lambda e, this is equal to 1. So here I use, of course, right, I use this spectral inclusion, right, to restrict the integral to minus r. This is equal to 1. Okay, so we can apply Hölder with powers 1/3 and 2/3 to this one. So we have that psi e to the minus I t a lambda phi by Hölder's inequality is bounded from above by, first we are going to keep integral, well, I don't write it anymore, but it's between minus r mu lambda psi t lambda e. And the integral of u lambda psi to the power, what power do I put here? Let me check that this is correct. 1/2 to the power 2/3, right? And of course this is valid for any t, right? Because this is just bounded by 1, so we can put the sup over t in here. Sorry, here I put this, right? And here there is a 1/3 method. Here we go. Okay, but this goes away. This is equal to 1. Okay, this one goes away. Okay, and now we write a lambda. We can write it as a lambda minus lambda, or a lambda 0 plus a lambda minus lambda 0. Sorry, plus not a lambda minus lambda 0, plus lambda minus lambda 0 phi. Right, we write this. And so we have that. We have that u lambda of psi can be written as minus lambda 0. We just use the formula you had before. A lambda 0 minus e minus I 0 inverse of psi phi. Right, phi psi, sorry. The limit exists. Right here we had the projection onto the eigenspace. Okay, and so plugging this into that equation, hence we get that the sup over t of psi e to the I t a lambda minus e t a lambda phi. This is bounded from above by, well, here what we get this to the power 1/2, 1/3, but this, right, lambda minus lambda 0 is of course, when lambda 0 is a point inside the support of G, right, and lambda also, this is bounded by the diameter of the support of G, so we get here delta to the 1/3, right, that comes out of here, so we have 1/2 and 1/3, and then you have still integral of a lambda minus e minus I 0, sorry, phi psi minus 1 to the 1/2, right, d mu lambda to the 2/3, and now what we do is, so this is the integral from minus r to r, and now we integrate in lambda, right? Now we integrate in lambda. So we take the integral of this d lambda, or sorry, g lambda d lambda of this, right? just taking this thing here. Yeah. Okay. And so we're going to take this. But now what we have is the following thing. We use again Hölder's inequality. If we take the expectation of f to the 2/3, this is less than expectation of f to the 2/3. That's again by Hölder, right? Writing f equals f times 1, and expectation of 1 is 1. Okay, so we get that if we take the expectation of d mu lambda, so if you take now this expectation, so that's the what I call E lambda, right? So this is what I call E lambda of dot. Now, I take E lambda of dot of this side. I take the same E lambda of dot of that side. Now I use this inequality to put the E lambda in here. Right? This, sorry, there's a lambda 0 here. This doesn't depend on lambda. It's only d mu lambda, right? So what I get is that I need to compute E lambda of d mu lambda, right? But this is given by the spectral averaging theorem, right? Because we know that this is bounded just by looking at this integral of g lambda d mu lambda d lambda, which is bounded by, well, a constant, the sup norm of g, integral of d mu lambda d lambda, which is, that's spectral averaging, equal to dE. So it's bounded by g. This is dE, right? So if you plug this in there, what you get is, well, E lambda sup over T of psi e to the minus I T A lambda phi is bounded by, so what comes out is lambda delta to the 1/3, g to the 2/3, and here you have integral from minus r to r of a lambda 0 minus e minus I 0 inverse phi psi inverse 1/2 dE. To the power 2/3, sorry. So the C is actually, C is this, right? Because I need to take, if I put the 3/2 on this side, I need to take a power 3/2 of that, right? So I get delta cube. I said, no, this is 1/3, not 1/2. So I multiply by 3/2, so I get delta 1/2, and I get G1. Okay, so that's correct. And now, once we have this, we want to combine this with the previous result. Okay, so application to the Anderson model. So of course we do the following. We write h omega equals a, which I call, well, h n, or h what I called before, I think, omega super n, plus omega little n delta n, right? So this is going to play the role of A. And now what we get here, right, what this gives us So what do we get here? What we get here is the following thing. So we obtain that E of, so we take omega n of sup over t of, so we can take psi equals delta m, right? Phi equals delta n. H omega. This is bounded from above by a constant, right? Times the integral over H. So how should I write it? I should write it in the following way. H omega, I'm going to write it this, or I'm going to write it explicitly, plus omega n, right? Minus, so, sorry, I'll write it this way. Omega n 0, I need to fix this one, times delta n, right? Where omega n 0 now is a fixed number. Omega n 0 is just a fixed number, right? It's in the support of G. N 0, and here we have minus E minus I 0, and we have delta n delta m 1/2 dE. And there is a 2/3 here. Okay, and now what I want is the following. Now I want to take, you see, I have the same thing here. This operator is the same as that one, except that I replace the omega n by omega n 0. And omega n 0 is free. It's a parameter I can choose. So what I can do is I can just take this inequality and integrate this in respect to d omega n 0, d omega n 0. Right? I take this inequality and I do this integral on both sides. Okay? So what do I get? Here, this is a constant, doesn't depend on omega n 0. I integrate, the total measure is 1. So I get the same thing. E omega n sup t blah blah blah, right? Sorry, what I'm going to do is I'm going to do something better actually. Yeah, okay, I can do it. I can start with this, but and then here I get the following. I use again Hölder, the same one as here, to slide the integral of omega n 0 inside. Right? So what I get is I get that this is less than c integral of, and here you have integral of, once I slid it inside, integral in d omega n 0. There's a bar missing here. Integral in energy of, in dE of h omega n plus omega n 0 delta n minus e plus I0 inverse delta n delta m 1/2. And here 2/3. But of course, I can also do the same thing with respect to all the other random variables, meaning omega m different from omega n. Right? I can do the same thing. I do the same integration. And if I do this here, and I integrate, so same thing, for omega, the whole of omega n. Right? For this vector, which is just a vector omega m for m different from n. I do the same integration. But when I do this, of course, here I get the expectation with respect to all the random variables. And here, well, I integrate with all the remaining ones, so I also get the expectation with respect to all the random variables. right? But this is exactly what we already estimated. We know that this is exponentially decaying, right? That the 2/3 is outside. We know that this is less than e to the minus eta, 1 over eta, times n minus m. Right? That's the previous theorem. That's exactly the estimate we got for the previous theorem, from the previous theorem. Well, here we are. It's finished. Okay, and what is important is that we get the same thing for finite cubes, right? For the finite cubes, you get the same thing. So for finite cubes, the fact to say that the spectrum is just pure point is an obvious thing, but actually from these estimates, you see that it is better than just pure point, right? You get some strong estimates on the kernels of, for example, the evolution group for this operator, or the resolvents, and from that we're going to deduce things about the eigenfunctions next time. Okay? So on Thursday we'll do the eigenfunctions, and then there'll be 2 sessions left. So one of them, the last 2 will be just one more estimate I'm going to prove, which is the Minami estimate. And the proof is quite simple. And then we are going to use the 3 tools to deduce the spectrostatistics. Right? And there's a general scheme. You'll see it's not very difficult once you've understood how you should go about it. Okay, I'm going to finish here.